All right. Hi, everyone. Thank you for coming. On today's seminar, we're going to have Tutku Kolku. She's a postdoctoral researcher at the University of Nottingham, working with the Euclid consortium. She completed her undergrad and master's degrees at the University of Birmingham, and her PhD at Liverpool John Moores University. Her research focuses on galaxy evolution, from gas cinematics and bar driving processes within galaxies to the environment effects of galaxy clusters. Her current work uses intracluster light to investigate the assembly of galaxy clusters and their dark matter halos. Thank you so much, Tutku, for accepting the invite. You may start whenever you're ready.
Sure, of course. Just to confirm, can you hear me?
Very well.
Great. And I also recommend you to watch this seminar with the lights closed because there will be some diffuse things that maybe you might not be able to see if there is so much bright light in that. But yeah, now okay, great. Thanks, Dana. Well, thank you very much for your invitation. I'm very happy to be giving this seminar to you. I wish I was there in person, but maybe one day in the future I can be there. So yes, I'm Tutku Kolku. I'm a postdoc in University of Nottingham in England. And today I'm going to talk about what I'm up to nowadays within my postdoc. But before doing that, as also you heard in the introduction, my background is within different kinds of things. So I would like to just introduce a little bit of what my research interest is currently and what is it going towards in the future before I actually talk about my postdoc position. So overall, my background is heavily extragalactic astronomy, particularly with observations. So I have spent quite a lot of time studying galaxies, nearby galaxies, particularly the processes that is influencing the gas in galaxies, like bars, star formation, AGN tech, and so on. So that was mainly what I have done in PhD, where I used Muse data, ALMA data to study these kind of processes. And nowadays, my interest is shifted towards galaxies and how they are influenced within actually groups and clusters. So my interest is shifting towards a bit more denser environment side. And I'm interested to sort of basically examine the processes and how are they being affected by the environment. And being in Nottingham currently, I'm also very much involved with more like large scale dynamics of that is influencing the environments, like the clusters and like even like how does the dark matter halo changes the environment and so on. So basically, I'm a bit of in the future, like in very near future, I'm trying to sort of merge all my interests under one umbrella. And if you're interested in this kind of things, it's a great time to study this sort of things because we have lots of data from ground-based observatories like VLT, ALMA, but also in the space, like, JWST is there, Euclid LSST is giving us much more large samples to focus on such work. And also we have much advanced hydrodynamical simulations now that we can validate our methods and studies. But yeah, so if you're interested in any kind of parts of this science, you can always email me and contact me to chat a little bit more about that. But yeah, as I said today, I'm going to talk about my postdoctoral research in Nottingham. This is the group I'm part of. We are all so led by Nina and also Stephen quite heavily. So we are all their minions. So we have lots of observers, also simulators, and we are probably one of the largest largest groups in England that is focusing on one particular subject, which is intracluster light. So besides like galactic, extragalactic, all of us are working in some aspects of the intercluster light, whether it's observational, whether with simulations or different types of data, we are all focusing on the same thing. And this is why we are growing every day in terms of science in understanding such great subject. Yeah. So coming towards my current research interest, I would like to first a little bit talk about dark matter in the context for my own research, also in the context that I understand because there is a lot of unknown about this. But nevertheless, so we know dark matter is the dominant form of matter in the universe. It forms about 85% of the matter. And what we know about it is that it's non-baryonic, and it's collisionless. So there is, so basically, it interacts gravitationally and grows hierarchically. What I mean by that, we know that from density fluctuations, the small dark matter particles can interact and collapse and form a little bit of a bigger dark matter substructures, which we call halos. So, for example, in this image that I'm showing from the Caterpillar project, this is a dark matter simulation. So what you're seeing here is just dark matter particles, basically just that is forming a galaxy cluster. So you can see these all circled parts are individual halos of the small galaxies, like basically satellite galaxies, but in the dark matter context. And at some point, all these small halos will collapse and form a much bigger, huge halo eventually. So things in the dark matter universe is growing hierarchically. And so basically my project is particular to study the shape of the dark matter halo. So what does the shape of a dark matter halo actually tells us? So we know in simulations, which I like to call them numerical experiments, depending on what you change in your experiment in terms of an ingredient will change the output. And the nature of dark matter that you choose is one of these ingredients. For example, if you choose self-interacting dark matter model in your simulations, you end up producing a round dark matter halo, and that does not have a core, because in self-interacting matter basically allows dark matter particles to interact and thermalize throughout the whole system. And this kind of causes energy exchange and dissipates the formation of a cuspy core. But if you were to, instead of self-interacting, choose a cold dark matter model, for example, like on the left, the dark matter particles there are not free to collide. They do not interact. Therefore, it kind of ends up forming a much more elliptical and density. It also forms a much more dense core. So basically, you can see between these two models that are being chosen in simulations, we end up seeing a different shape that is being projected to us in the dark, as a dark matter halo. So this tells us if we study the shape of the dark matter halo in simulations, we end up knowing a little bit more about the nature of the dark matter particle itself, whether if it's interacting or not. So this is why people have been focusing on different sort of dark matter models being basically part of their simulated data. But this aside, I want to come back to intracluster light. So why we should actually, what is intracluster light, and what does the shape of intracluster light actually mean in the dark matter context? So intracluster light is this diffuse glow that you're seeing in the Perseus cluster, for example. So it's the diffuse stellar glow in the galaxy clusters. And similar to dark matter, it is collisionless. And basically, I'm going to come to it, but it has different types of formation channels. But overall, what is growing intracluster light is the stripping of the material from individual halos, so basically the satellite galaxies. So this material leaves the local halo of the individual galaxies and starts to follow the gravitational potential of the whole cluster itself. And this is why it is believed that it is taken as that intracluster light is one of the luminous probe of the dark matter halo of the galaxy potential because of its assembly and because of its nature being collisionless. So there are many different types of channels that is contributing to the formation and the growth and the shape of the characteristics of intracluster light. So disruption of dwarf galaxies, stripping of massive satellite galaxies within the clusters is one of the main contributors. Basically, it's just like these galaxies just falls into the galaxy cluster. And throughout the time, there can be relaxations and mixing. So this material kind of like calms down and settles within the gravitational potential of the cluster. There can be groups that are interacting with one another, but also all together falling towards the cluster itself. This is another sort of contribution, complex contribution, but also in situ star formation. So as we said, the material is being stripped from individual galaxies to the entire system. And this usually that this material, it can actually being stripped as a, like maybe a thread or a knot and so on. So it can still continue to form stars within itself as it also goes and propagates within the cluster. So all these complicated basically channels, if I can call these as channels, all these complicated processes and channels makes the intercluster light very important, because then studying the intercluster light characteristics, then you can learn about the merger history of the clusters and maybe like what sort of interactions it has undergone throughout the entire evolution of the cluster itself. So it's a very important channel. And as we said, it's collisionless and is taken as the luminous probe of the dark matter overall. And this brings me back to these two figures I've shown you before. So basically, as we said, studying the shape of the dark matter halo in simulations teaches us about what's the nature of the dark matter particle in general. And since we are claiming that intracluster light should be a dominant tracer that is basically tracer of the dark matter halo, if we study the shape of the intracluster light, will teach us about the shape of the halo, and the shape of the halo will teach us about the nature of dark matter. So this is basically the main motivation behind our research in studying the shape of intracluster light. And for example, this I would like to talk a little bit more about recent simulations and what do they tell us about ICL, intracluster light, and dark matter tracing one another. This work I'm presenting the plots from is work from one of our PhD students, Adela Fernandez, where she used Hydrangea hydrodynamical simulations to study basically whether intercluster light and dark matter traces one another. So what I'm showing you is in the first plot, we have the BCG and intercluster light, basically just the stellar particles from the simulated data for low and high mass regimes, low and high mass cluster regimes. And in the middle, you are seeing the dark matter distribution. So basically, only the dark matter particles in the simulation, and how does what's the shape of the dark matter basically. And the last panel is the offset between the shapes, the two distributions. And what I have included here are these vertical streaks. So basically, that's just me telling you about which region is BCG dominated, basically which region is dominated by the brightest cluster galaxy within the galaxy cluster, which is this dominant galaxy, basically in a cluster environment that everything is being collapsed into. So basically left to this region is the BCG dominated regions, and to the right is basically the more or less intracluster light dominated regions. So what these plots are basically telling us, if we look at the offset, is that within the intracluster light region, the dark matter and the BCG and ICL, so the stellar and the dark matter halo shape is flat. So and this is the case for the both high and low mass clusters. So basically, based on such simulation data, we can trace ICL shape and the halo dark matter shape all together, and they will correspond to one another. So we can understand dark matter halo shape using the intercluster light as well. And observationally, there has been similar work as well in order to understand why does ICL, in order to see whether ICL traces the dark matter or not. But this is a little bit more tricky because in simulations, you know what is dark matter particle, what is stellar particle, and you can isolate them very well to study one another. But in observations, that's more challenging. So one of the closest probes or tracers, if I may say, to dark matter potential is coming from the lensing measurements. So the gravitational lensing works in a way, so if you have a galaxy cluster and a background galaxy that its light is crossing the entire cluster system and then bends, so what you see is these lensing arcs, but in order to be able to measure that light traveled to the entire potential of the cluster itself. So instead of just the projected information from lensing, we can infer a more three-actual, more 3D information about the potential of the galaxy clusters. So this is why they are mostly taken as one of the best tracers for the dark matter potential of best tracers of the dark matter potential in the clusters. So what in this work from Mireia Montes and Nacho Trujillo, they have basically looked at different probes of the dark matter halo. So they have studied intracluster light, they have studied the lensing masses, which is basically what I just said, it's coming from the gravitational lensing. And they have also looked into X-rays. So X-rays is another powerful probe if you want to measure the mass distribution of your cluster, but it's a little bit tricky if your cluster is interacting or it's unrelaxed because X-rays are more thermally influenced. So within an unrelaxed cluster that's interacting, the distribution of X-rays might be more random or chaotic towards wherever the collisions are happening, rather than more relaxed, what potentially halo would do. So they have basically compared the contours of the different tracers and saw which one is actually more close to the weak lensing mass. And they have seen that, I think they have studied about like maybe 10 galaxy clusters, and they've seen that intercluster light distribution is much more close to the lensing mass distributions compared to X-rays. So that's one of the claims that has actually brought the intercluster light being tracing the dark matter halo of the cluster is a bit better than the other probes like X-rays. Okay, so this all brings down the motivation we have in order to study the intercluster light and particularly to focus on its shape. Because now it's a good time to do such studies because we have Euclid being on the act. So Euclid is a white sky survey. It's basically it's an ESA NASA mission. It's basically covering 1/3 of the sky, which is about like 15,000 degrees square. And currently we are given data from a quick release, which basically has been 2 years that we're working on such data. And that is basically these tiny yellow patches within the blue regions that Euclid's meant to cover. So basically we have data from 50 degrees squared of the Euclid. So in terms of data, we have data from 4 bands, which is I band, which is basically like a wide visible coverage. And we have Y, J, and H near infrared bands, if you see on the wavelength axis. And Euclid's main mission is actually cosmology. So they want to get accurate lensing masses, they want to get accurate redshifts, and those sort of measurements. So they don't actually care much about diffuse light. But because it's very deep, it can get very deep, it's actually also a great ICL detector. And there are many people that do dwarf galaxy work with Euclid as well. So it's actually quite good in terms of capability of detecting faint light. But it's important that it's a cosmology mission because I'm going to show you in a bit what the data looks like if they do not care about the diffuse light. But so overall, recently within the group I'm working with, we have we have published several Euclid quick release data papers, and they will be very soon on arXiv. There is a lot of bureaucracy within Euclid, so they're not out yet. But they're accepted, they're waiting somewhere to give us okay so that we can actually share it with the world. But in particularly the work I was leading, we are, as I said, focusing on the shape of cluster halos, but also particularly focusing on the Euclid sensitivity in detecting those sort of signals. And basically, this is what I'm going to talk in my next slide. So in this study, we particularly focused on, as I said, quick release data. We had about data for 200 clusters from DES and eROSITA surveys. So by the time we started to work with this data, we didn't have any cluster catalogs from Euclid. So we kind of brought together a hybrid catalog from the eROSITA. And this catalog had clusters that are really massive and within the redshift range of 0.1 to 0.8. But it was actually a good data set in general because we've seen that we had a lot of variety in terms of the shape morphology. You can see some clusters are more elongated, some are more like a plate shape, some are more round. So it was a good test study to check our measurements, to check whether our shape detecting methodology works or not. And then once the data release one comes in, which basically we have just started to receive the data and we are in terms of processing it, we will actually have about 100,000 galaxy clusters where we can detect the intercluster light. So the entire, all the plots that I'm going to show you are basically part of the test study, and we are going to improve their accuracy to a much higher level within the coming data release. Yes, so this is an important plot about why we should care that Euclid is a cosmology mission and not a low surface brightness science focused mission. So as they do not care much about the diffuse light, they can do as much as aggressive processing as they want to. So in the Euclid archives, they also provide us with the science products, data products. Basically, like the entire sky can be mosaicked and so on. So you have all the information you want. But they do very aggressive background cutting, which is very important for us in ICL sciences because ICL is very extended and diffuse. And if you do not be careful, your ICL signal basically will be over subtracted by the background signal that you are trying to correct. So you can see on the left, we have a standard final Euclid product that you can go on the Euclid archive and select the cluster coordinates, and that comes up basically. But first thing to notice, there is much less intracluster light within this cluster compared to the right-hand side where it's our processing of it. But there are also a lot of artifacts inherited from the instrument itself. So there are like persistent streaks. I don't know if you can see, but it was very difficult on the screen before. So there is like sort of like a square tartan pattern grid in the background where we also have to correct for that. There is inconsistencies within the background level, flux calibrations and so on. We have stars. Now we are also removing the stars, but not on this image particularly. But so basically we've spent an entire year, particularly Stephen Bamford had a huge effort, like a heroic effort on such correction in order to bring the output we can study to output images that we can study ICL from left to right. So you can see much more extended emission is being preserved, and we know exactly what is our background limitation because we are actually the ones that are doing the corrections and so on. We got rid of the many of the artifacts that is inherited by the instrument itself, so that we can basically be as minimum, so that our measurements can be contaminated as minimum as possible. So once Steven gives us these images, then I can actually take over and do some measurements about intercluster light. So what I do first is that, so this is an example cluster that I'm also presenting in the paper. So on the right, on the left, you can see a composite image created by the I, J, and H bands of Euclid. And on the right, we are only seeing the H band. So first thing to do is for me to basically just do a median background calculation in order to basically isolate the sources to mask them. So masking is very important before actually calculating any flux or shape measurements. So we have, and depending on what fraction of the objects you are masking is also very important. So towards the outer regions of the cluster, we have to do it adaptively, so that basically we cover the source, but also amplify it a little bit to cover the sort of adjacent spaxel to the source to ensure that all the source is being taken taken away before the measurements of the intercluster light, so that that flux is not being incorporated within that diffuse signal. So by eye, it's very difficult to see. This is why we have to do it adaptively in general. And within the BCG halo, so basically within this 0.1 or 200 region, we do it a little bit less conservatively. So the fraction of sources that grows is adapted depending on where the source is and depending on also how large the source is. So for example, this huge star is growing a bit more compared to the other point sources that are less extended overall. So we had also quite a lot of tests about our masking strategy before we actually applied it to the rest of the sample. But eventually I isolate only the BCG, the dominant galaxy basically in the cluster, and the intracluster light only within the image. And I use a fitting software called Autoprop, which is basically an elliptical isophotal fitting software that first calculates the isophotes uh, within the cluster itself and then forces that to be an ellipse and kind of regularizes it to find the best fitting ellipse to that isophone. And that in return gives us the position angle, basically what sort of how does the light is oriented towards what's the axis, the major axis of the light, basically, how elliptical that fitted shape is, and so on. So what you can see in this image on the right is that the fitted ellipses, some of them are dashed, some of them are solid lines. So that actually has a meaning in this context. So all the way out to solid lines, that's signal to noise ratio of 5. So this is basically the last radius where we can actually measure the shape robustly. And out there from out that radius, we are dominated with the background noise so that we cannot actually constrain robust shape. So we kind of stop the shape measurements there, which we call our shape, very creative. And out to there, within the dashed lines, we extrapolate the exact same ellipse within the same increments that we have used, just to calculate signal to noise. Because despite we don't see the shape of the ICL, we can still see the signal relative to the background noise. So we still extract it all the way out to the image edge. And then we, after that, we kind of calculate the noise as well, amplify the noise to 3 sigma, and then to sort of calculate a 3 sigma intersection with the actual flux to find where actually we can see the extent of the ICL signal overall. So this is going to make a bit more sense in these plots, I believe. So what we have, basically, we have a radial position angle. So basically the angle of these ellipses that are fitted all the way out. Ellipticity, again, radially, radial distribution, and the surface brightness. So basically, each point here corresponds to the flux in each annulus, all the way to the edge of the image. But you can see they get more noisy with the background being dominated. The dotted lines here are the sensitive noise calculations that we have to go through within a large Euclid sky patch. I can talk more about this if you're interested after the talk, how we calculate the noise. But basically, we calculate the noise level and times it by 3, which is a common value to use, basically just to ensure what we are extracting as the last flux measurement is sensitive enough with respect to the background noise. So in this example cluster, for example, we can trace the shape out to about 100 to 200 kiloparsec, which is actually the case with the whole sample we have. And we can detect the ICL signal out to 4 to 500 kiloparsecs down to about 27.5, 28 magnitude limits. And we have looked at the sensitivity of different Euclid bands to the shape, and we noticed that they're more or less very similar. So we have used H band as a reference band basically to trace the shape, because that was the band that is tracing the ICL signal and the shape to the furthest point overall, because ICL is usually redder, so it wasn't much surprising to see the reddest band of Euclid is probing it a little bit to larger degrees, but basically we have taken H band as a reference band throughout the rest of the talk. And about in 70% of the clusters, we could trace the shape of the ICL out to 100 kiloparsecs. Okay, so obviously because we are very well, we are overall concerned by, like the methodology, how it has to be validated and so on. Intercluster light measurements are very sensitive. So we had to do some simulation comparison in order to validate our methodology and to make sure what we are measuring is actually robust enough. So as I said, we have many people also in Nottingham that focuses on simulations. So particularly, Yannick Bahe is the Hydrangea simulation PI, so he helps us a lot in terms of obtaining simulations, basically. So we have done some tests. So we have overall, just to give you a perspective of what kind of simulated images we work with. We have the perfect images, which is basically BCG and the ICL light, just almost like a very Surdic distribution. We have the same thing, BCG, ICL, but also the satellites. So the individual halos, basically the satellite galaxies that would be in a cluster. And we take this middle panel and make it so it passes through some SCD fitting and so on to match the Euclid standards, and we place it to a Euclid random sky location in the Euclid sky. And then we pass it through the same masking, background matching, and so on. So the entire methodology applies to these simulated mock galaxy clusters, basically. And then we go through the same shape measurements and so on to extract the shape of these simulated clusters to see whether if it matches observations or whether there are any biases. Because in principle, these perfect shapes that we have are the true shapes in the simulations. And we want to see how much that will actually differ if when we forward model and put things in an observed frame. That actually comes to an interesting point. So what we've seen is there are so many histograms, so I'm going to go one by one. So what we have first is the red histogram, which is the observed distribution from observed clusters in Euclid. So there are like 130 clusters in this image. And the yellow one is a lensing study. So it's a distribution from weak lensing shape measurements. From a study that had a very similar sample, very similar redshifts, masses, and the number in terms of that to our observed sample with the Euclid that we used in this study. And you can see that their median is basically almost the same. So they're a very well matching distribution between themselves. However, then we also had to look at the unbound ICL, so basically the BCG ICL, that perfect image shapes. And we have seen that actually that is very round. So the distributions we are obtaining for the ICL ellipticity in those images are much more round. And we have the blue one, which is the forward model. So when we put the simulated data to a real sky, we actually observe a bit more elliptical shapes. So basically between the dotted and the blue line, we would expect to see some sort of alignment, but at the same time, we are seeing that basically our results are biased towards more elliptical values. So a simulator will be like, well, you are biased, and that means the weak lensing measurements are a little bit biased, but then you will talk to an observer and they will be like, oh, how much I trust the simulation data anyway. So like, there is this still degeneracy that is being held in these histograms overall. But overall, we liked the agreement between the Euclid and the lensing measurements because as weak lensing is counted as the ground truth, despite it is a little bit biased, the agreements between the two distributions are still telling us that ICL is tracing the dark matter halo overall. But it is important to keep in mind that there is some sort of elliptical bias in terms of the literal numbers that we are seeing. So since we had only 200 clusters, one thing that we could do is to, I mean, despite the number that you have overall, doing stack analysis actually teaches you more about the collective information that is being grouped underneath some characteristics. So you can do like mass stacking, so you can basically pick clusters that are at the same mass. You can do redshift stacking, that they are at the same redshift. You can just pick very elliptical clusters and stack them to learn a bit more about them overall. But within the 200 clusters we had only be able to do redshift stacking because we didn't have too much of a mass spread to have a look into like what would be happening if we had like really massive clusters and so on. So we have limited the sample to a relatively similar range of stellar masses, well, halo masses, and then basically grouped them within individual redshift bins, as you see here. So from 0.1 to 3, 3 to 4, blah, blah, all the way out to 0.8. And roughly each of these images roughly consists about 40 to 50 clusters. So what we did to these clusters, the first thing to do is to rotate them in such that their ICL position angle that we have measured is aligned. Because if you don't align them together, that will end up just being a round measurement at the end because you're kind of like aligning things that are random oriented. So we had to rotate the clusters in such they have the same, their position to the same axis. And then we just basically median combine them or sigma clip combine them. You can do whichever you want. And we basically, after stacking the clusters, we have done very similar measurements to the, basically just measured the ellipticity of the isophotes again. So what we've seen is that so within the average cluster sample, which is basically if we just average all the profiles of the individual clusters, we would, as I said, we could only detect the intercluster light out to about 100 kiloparsecs. So what we've seen in that average distribution is we saw that the central regions are of all the clusters are more round comparatively, and things get progressively more elliptical towards the outer regions. And in the stack sample, the shape kind of holds. So in all the stacks, we see more rounder BCG-dominated regions, and it gets comparatively more elliptical all the way towards the outside. And unlike 100 kiloparsecs that we've seen in the average clusters, we can stacking improves that signal out to about 0.4 to 0.5. Well, mostly 0.4 or 200. So you can actually detect the shape of the cluster halo out to 400 kiloparsecs in almost all redshift bins. So one thing that we were not very happy with this plot is that we see no redshift evolution. So humbly, we assume that because we are tracing from redshift 0.1 to 0.8, there should be a redshift evolution because things that are at higher redshift that are they're less relaxed. So they should have been a bit more elliptical compared to the other compared to the lower redshifts. But maybe it's our sample size being small. Maybe it's because maybe 0.1 to 0.8 there isn't actually too much of an evolutionary change within the clusters that we had. We do not see that evolution in observations. And we don't see that in simulations either, despite there are much more clusters in simulated data. The parent simulations are actually just 24 main clusters. So we amplify the sample size by just projecting those parent to 24 and placing them at different redshifts in order to just obtain more clusters. But that still intrinsically tells you that the shape might be depending on such analysis. So overall, what we've learned about the Euclid is that it's powerful. So it's going to be much more prominent and much more interesting when we actually have those thousands of clusters from the data release one. But it is very powerful in detecting the intercluster light signal down to 20.7, 27.5 to 28 magnitudes, mostly in H band and also R band. And we're going to be able to detect ICL shapes out to 400 kiloparsec, even for redshifts like at 0.1 at this point, roughly. So it's going to be very interesting in the future to see what is going to come out from it. So this is my conclusions. I'm happy to take any questions. And that's it. Thank you.
Thank you, Tutku. Do we have questions? Miro.
Hello, can you hear me?
Yes.
It was a very interesting talk, but what interested me most is the reprocessing of the images that you did using NICL, if I'm not wrong.
Sorry, I'm gonna ask you to slow down a little bit because the voice is coming all together. So there is like sort of an echo. So
He comes close to here.
Now is it better?
yes, I think so.
Okay, so the image that you showed, one that was processed by Euclid consortium and then the one that you reprocessed it again. So in
Yes.
the central part was saturated, but then once you reprocessed it was fine. So what exactly the reprocessing is which led you to more clear?
Yeah, you're right. So I actually didn't say that. So in order to be able to bring the image to the right, we actually had to start from a level of data that is not processed to this level yet. So we had to start from a more raw data. Still not, it wasn't the rawest that we could start with. So we start from an earlier stage of the raw data, and we do like bunch of different things, like matching different dithers of the instrument. It has 4 dithers, so it observes the same location of the sky by at a little bit of a different angle,
Yeah.
4 times. So we had to do matching between those different dithers. We had to do flat fielding, like a super flat across all things. So we had to do basically very basic photometry, but it was very complicated because of those 4 dithers and a huge data set that you're actually trying to correct everything at the same time. But so we did not process the image on the left to make the right. We actually had to process it from a much rawer data
Okay.
in order to bring it.
So
Was
in the raw
that your question?
yeah, sort of. Like in the raw data, it was not saturated. It was somewhere in between the process. It altered
So
the.
it's actually the data is what you're seeing on the left is actually not saturation, it's over subtraction. So the darker regions that you're seeing around the cluster is the regions where basically the background is over calculated. So you're just removing the signal from there. So it just too much signal there, and then so it appears negative. So there isn't much of a saturation there.
Okay. Good. Thank you.
More
So this is actually being discussed in Stephen Bamford's paper that is coming up very soon. So if you could just keep an eye on that, it's going to cover the entire processing steps that we have done for the Euclid data.
Okay, are there any questions? I have one. Keep thinking. Can you talk a bit more about the simulation forward model and how is that done?
Sure, as far as I can. So basically, we first have a perfect ICL distribution that is basically just the stellar particles in the Hydrangea simulation. And basically within the simulations, they have certain sort of like initial parameters, like how much this cluster is basically bound all together. So they form a BCG. That's the way I understand it. So I'm just going to talk about the way I understand it. And we have the BCG axial and the satellite. So they can also pick actually individual subhalos that are bound to themselves and not just the cluster, and include that back in. And then we take this middle one and we it has to pass through an ECD so that it actually matches the wavelength and the flux levels of basically Euclid. So that if I were to just take this middle image from the simulations and put it to Euclid sky, you will not see anything because the flux isn't calibrated. So it has to go through those sort of like ECD fitting ECD corrections so that it matches the same flux level as the Euclid would have. And we basically just, it's one on top of the other. So it's just like basically a co-addition of the two images. And in terms of the sky, we have selected a huge sky patch, which also we calculated the noise with it. So it's a sky patch that is very minimally contaminated by other clusters. So it's just basically like an empty sky region. And we make cutouts from the sky and just sort of like match it in such that basically we just co-add the middle one to we add the middle one to that sky cutout and form this sort of like a mock cluster. And then from there on, it goes through the exact same procedures as it would be an observation. So we kind of fancily called it forward model. We couldn't know what to call it. But yeah, this is the way we are like. So it's basically a simulation inside a real observed sky.
Okay. Thank you.
Yeah.
We have a question from Thaisa online. Thaisa, just
Hi,
go
thank
ahead.
you very
Hello.
much for your presentation.
Thank you.
My question is, you mentioned that you didn't find any evolution, but it seems to me that the redshift range is not so big, right?
Yeah, exactly. So actually, so with the data release one data, we want to, not that we want, so we have a forecasting paper that has actually did some modeling and simulation checks with the Euclid data before the actual data release came out. And they can show that we will be able to see ICL to 3 sigma out to redshift 3. But by the
Okay.
time we have actually started with the quick release data, we didn't have a catalog for higher redshift clusters. And so because of that, we just added the ones we have. So it was basically 0.1 to 0.8. But in
Yeah, maybe if
principle,
you add,
we should have, yeah, exactly. Once we actually include all of
Okay.
them, so that will amplify the overall number of the clusters and also the redshift range. Then maybe
Okay.
we can see some evolution.
Okay, thank you.
Do we have more questions? Basilio.
Can you hear me?
Yes.
Yes.
Okay. So the claim that ICL traces the dark matter distribution seems so far to be based on comparing shape parameters and this type of thing. I wonder how many cases of clusters with individual measurements of dark matter distribution through lensing and at the same time ICL distribution. How many cases of such clusters are there for a direct comparison to be possible?
Well, so firstly, in terms of just so the comparison of ICL and dark matter is not only done with the shape. So I've only showed it in that context because I'm focusing on shapes, but people have been doing studies on energetics like momentum, energy, and so on with simulated data to see whether intercluster light and dark matter has actually similar energetic characteristics. So there are a bunch of those sort of data as well that is showing promising results in terms of ICL and dark matter prominence. So there are also controversial results too. You can always find several, also within our group as well, to be honest. But there are much more than just in structural characterization of the things. In terms of, so sorry, so if I come back to your question about lensing and observations, would you mind telling me again?
Yeah, the thing is, there might be clusters, or perhaps in the future there will be more clusters where the distribution of dark matter is modeled by lensing, strong or weak
Yeah,
lensing.
I mean,
And also the ICL is modeled in a thorough way. And then you can make a direct comparison for those individual clusters of how one traces the other. So that's
yes, so one of the main deliverables of Euclid actually should be more lens clusters. So
Yeah.
they want to do more lensing like lens cluster, whatever catalogs. So that once we have those, So like it's just that there are so many groups working on different things, so it's a little bit hard to kind of bring all of them up to speed. But so in principle, we will have those weak lensing maps. Plus, the clusters like just inherently found with Euclid as well, with more accurate spectroscopic correct identifications. So we actually can have like a coherent catalog of clusters that are showing weak lensing or not showing, and basically all coming from Euclid. So far we don't have that. At least like they're not shared with us because they have to be first shared within the subgroups. But yes, you're right. So in principle, there will be much better catalogs in order to do that. So with data release 1, we are aiming to get out the ICL catalog for the entire Euclid, like 15,000 square degrees eventually, hopefully by the end of 2027, because now we have the data, we are processing it, and the catalog will take a while. But I have no idea about lensing measurements from that end of the collaboration. But yeah, there will be much more for sure.
Thank you.
More questions. We have time for a couple more. So I have one about how do you guys process this data? Do you use like the cloud of Euclid, or you download the data to a server in your university? How are you dealing with these?
That's a very good question, because that is a lot of data. So with Q1, just 50 square degrees, we were already struggling. But now we started with the DR1. We have to do it like band by band, I believe, which is a pain because you kind of have to process things at the same time if you want to do like a co-additions and so on. So currently university hates us, but we also hate the university. So it's kind of a both ways thing. So yeah, so they cannot. So, but overall, in terms of power, we are using the server of the university, which was actually underused until we came along with more data. But in terms of power, it's not a problem. But in terms of like storage space, I don't know. Steven has that, so like I'm the one that I'm like usually okay, give me the data, I don't care, or like I'm not gonna be able to install something because I run out of memory. But yeah. It's very difficult. So Euclid itself also has its own sort of I don't know what do you call it, but like they have their own
Data lab?
scripts and codes. They have something called data labs that you don't have to download the data to process it, but you can still process it. But it's a bit difficult for us because we have to have like a lot of products in order to bring them together. But in principle, if you're doing more cosmological things, maybe it's actually much lighter to do.
Cool. Thank you for sharing the real life.
And this is the end I know. I don't know what Nina knows. I'm scared.
Okay. So if there are no more questions, you can always email Tutku if you have
Okay,
follow-up.
yes, please do. Yes, I'm happy to. It was a lot of information. I'm happy to discuss anything further or just say hi. It's fine.
So I have one more question, but I'll just email you. So thanks a lot. Let's thank her again.
Thank you. Thank you for having me. Bye.
Bye-bye.